And welcome to C++ Bytes. In this video, we're going to talk about memory management and object lifecycle in C++. So you may already know that memory management is a very important aspect of programming in C++. And any kind of program you're writing, you pretty much have to understand what is the memory model, and also how it's managed, because a lot of times you have to manually manage it. And when I say a lot of times, it's pretty much most of the time, but sometimes it's managed for free for you, or you can use some utility classes which do it for you or make it easier. So it's very important to understand. So this video and the next one are gonna basically touch upon memory management, which is very important. This video is gonna be much more lower level memory management concepts. So we're gonna talk about stack, heap, constructor, destructor, virtual destructor, and then pointers and references and objects. That is kind of the big bucket of the language level memory management. And then in the next video, we're going to talk about some utilities we could use which can help us manage memory better. So let's get right to it. So I have a new project in VS Code. What I'm going to do is I'm just going to add a new file, and we're just going to I guess we'll just use one file, because this is mostly about trying different things and not necessarily about structuring our program. So we're going to keep it in one file so we can easily make changes. So what I'm going to do is I'm going to start with the main, which is our term 0, and then I'll probably include some utilities because we'll probably do some std out. So what I'm going to do is, let's say, so we want to basically we want to see how stack and heap are used and how we can utilize them. So just to explain, stack, as I explained in the previous video, every time your function gets called, either it's main, or you call another function, you call a function on an object, the arguments are pushed on a stack, and you basically have access to a stack which gets popped when you return. So it is temporary, and you can overflow the stack if you use too much of it, but it is pretty fast because it's handy, it's right there. So you can use it for some temporary variables, small kind of things you want to save, local storage, and stuff like that. So that's stack. The other memory pool which you get in C++ is referred to as heap. That is more bigger blocks of memory which are used mostly for objects, or if you need bigger chunks of memory allocation, which can stay during the entire life of the program, and it's up to the programmer to manage them. So you can allocate, and then you have to remember to deallocate or free it so that the memory manager can give it back to somebody else. If you don't free it, it stays occupied. And so those are the two things. For stack, most of the time it's managed for you, so the stack is cleaned up. But if you have something on the stack which was pointing to something on the heap, that thing on heap is pretty much gone. You don't have a pointer to it. It's still in the heap, it's not gone, but basically you cannot go ahead and release it because you lost your access point to it. So those are the two major chunks of storage types. So based on those storage types, the way you use them is by having different types of variables. So you have variables which can point to memory in the heap, or they can point to things on your stack, and that's how you manage them. So we'll do an example and we'll kind of work through all different examples. So let's start by creating a couple of classes so we can see how it works. So what I'm going to do is, let's say using namespace std. So I'm going to create a class and let's just call it grandparent. So we can use it for inheritance. And then let's say we have a class called parent, which is inherited from grandparent. And then let's say we have another class called child, which is inherited from parent. So this is going to be our hierarchy. So for the grandparent, let's say what we have is we have a string message, and I'm going to make its constructor protected. So the protected is a keyword you can use so that things that are protected, children can use it, but outside people cannot use it. So it's a good middle ground if you want it to be accessible during inheritance. So I'm going to have a constructor for my grandparent, which is going to take a message, because that's kind of what we want. So I'm going to say message is equal to msg, and there it is. And then let's say we have a method which called setMessage. So if you want to change the message, you can do that. So let's call it msg. And then let's say we have another method called printMessage. And I'm going to say there's no argument to this, and it's just going to go. And it's going to say cout message and line. So this is kind of the functionality we want. And what I'll do is I'll just add a destructor. We already talked about it in the last video. And this time I'm going to add a deleting grandparent, and then I'm going to add the message here just so that we know which one it was if we have multiple kind of messages. Okay, and so let me make a little room. And so I think at this point our grandparent looks good. Let's just fill up our parent. It's not going to have much, but we also don't want the parent default constructor to get called. So I'll do this. And let's say we want to have a similar kind of constructor, string msg. And, we want it to be empty. But the way you call the parent constructor, or super in some languages it's called, super, is you just call it like this. You can also call it the body sometimes, but so that way we called grandparent. We're saying, okay, when this is called, call this first with this argument, and everything's okay. And the other thing we want is we want a destructor, which would do kind of the same thing, deleting parent, and then I'll do message and line. And I'll do the same thing. It's a little bit of repetitive, but I think it's okay to do it. It's a little bit typing, but I'm okay typing a little bit. So I'm going to do child, kind of same thing, msg. It's going to call a parent instead of grandparent, and then it'll have a destructor. This one I think I can just copy paste here. And deleting child, and they all have access to message, which comes from here. So at this point, we have our 3 classes declared. So let's try to use them. So the first one I'm going to show is, so we're going to talk about 3. So we're going to talk about pointers, we're going to talk about objects, and we're going to talk about references, and we'll see what the difference is. So the first kind of simple one we know is, we've done it in the past, we have a child object, and I'm going to call it child object. This is the message. So this is an object that's created on the stack, and it's on the stack. Once the method returns, which is main at this point, it will get deleted automatically. So let me compile this, make sure it works, and let's try to run this. So I'll do main. You can see it deleted child turn with the message child object. So everything's good at this point. The second type I want to talk about is a pointer. So a pointer is a variable which points, which does not contain the object itself. It contains an address to an object. So the way pointer works is, if you have an object A, let's say, the variable, the pointer would just point to A. So object A would have its values in it, but the actual memory address, the address of this object, would be the contents of the pointer. So let's say you have an object B, which is stored at location 1. And if you have a pointer A which points to B, so the contents of the pointer would be location 1, whatever is the location of object B. So that's kind of how the pointers work. You can read more about them. They're not as bad as people think they are, or complicated, but it does get some, you need to get used to them, and it's a lot easier to make mistakes and have null pointers and stuff like that. But that's what a pointer is. So the way you would use a pointer is, you would have a variable child pointer. So this, I'm saying, this is a variable which would contain the address of a child object. It will not contain the child object, it would be the address. So I'm going to say child pointer equal to, so this is the syntax, new child, and I'm going to say child pointer. So what this new child does is, it creates an object of type new in the heap, and it returns the address. So that's why you assign it to a pointer, because it's an address. So now we have the address of this object. Now, just to show the stack and heap behavior we were talking about earlier, if I was to run this program at this point, you can see that only one object got deleted. The other object was leaked, which was the pointer. So we have a whole object which is not deleted because it's in heap, and the programmer is manually responsible for cleaning up the heap. The stack gets taken care for you. So the way you clean up, so this is the way you would create an object in the heap. You use the new keyword, and the way you delete it is, you use the delete keyword. You say delete and give child pointer, and that's it. You do this and you run through this, and now you can see that it deleted everything. So at this point, we're cleaning up the memory and everything's okay. Now, one thing, given that we're talking about pointers, I want to mention, which I have been ignoring up till this point, is the thing with pointers is, you can typecast them. So what you can do is, you have a child pointer and you can change it to be a parent pointer. So you can say parent ptr is equal to, and you can say make it a parent pointer, and you give it the child pointer. So what you're saying is, okay, I have a child pointer, but I want it to be treated as a parent pointer. Now the object which it points to, they both point to the same object, which is of the type child. So the object is always child, but the pointer which points to it has a different type here. Here, the compiler saying, okay, this is of the type parent. Here, the compiler saying it's of the type child, while in reality, in both cases, it's of the type child. Now what happens is, if we were to change this code like this, and instead of deleting the parent pointer, we were to say delete, instead of deleting the child pointer, we were to say delete parent pointer. Now what happens is, it's probably easier to show than, so I'll run this, so you can see that the pointer has only 2 delete lines and the object has 3 delete lines. Now what that means is, because the thing we're deleting has the type parent, it starts deleting from the parent. Then it goes to grandparent and it's done. It does not delete the child, or at least does not call the destructor of the child. Probably deletes the object. So now you can see this can cause some bugs. If you have to do some important cleanup, it would not happen unless you use the right type here. So if you use child pointer here and run it again, now you can see the right thing is called. So the way you fix this, let's go back to the buggy code and let's make sure it does what it was doing before here. So the way you do this is you make the destructors virtual. So you just add the virtual keyword to all the destructors in the inheritance chain. So what that does is it takes away this behavior that the type of the pointer dictates which destructors get called. So now, once we added virtual, we have the same code. If we run it again, you can see it called the correct hierarchy. So this is one important thing to note, that if you have classes which inherit, it's probably a good idea to have all your destructors virtual. That way, if somebody uses as a pointer, or somebody uses an object, or somebody uses a typecasted pointer, they don't have to worry about which destructor gets called. All of them would get called, they would be involved for cleanup, and everything would be managed properly. So that's just something I had to include at this point, because unless you see this behavior, it's not obvious what might happen. So I hope it's clear now. So at this point, this bug is gone. We can just go back to our child pointer and it should behave the same. Let's just make sure it does before we move on. Okay. So now you've seen a pointer and you've seen an object. So there is another type which is called a reference. And the syntax to have a reference is this. So you can do a child ref is equal to, and the reference can point to any object. And so what I'll do is I'll create a second object for the reference for ref, and I'll say child or I'll call it child reference. So you can assign it to this guy, and that way it always has a value assigned. So you can see it also holds the address, just like the pointer here. But you can have it, to an object, and you don't have to do the memory manipulation or address and stuff like that. So the way references work and pointers work is, it's probably better to show with an example. So let's do this. So let's add a method called change message. And for one version, let's say it takes a child object and it takes a message. And then all we do is we say child obj.setMessage message. So this is a utility method. It's not in any class, and we're just saying, okay, we'll call it, we'll give it an object, it'll change the message of that object. Let's have another same kind of method with different arguments, and I'm going to say child pointer. It's going to have string msg, and then same thing, child pointer. And to show you the syntax, if you have a pointer, you can't do dot, so you have to do this arrow, so that way it would go get the target object of the pointer. So child pointer has an address, you do this arrow, it dereferences the address, gets the object, and then it tries to call the method you want. There's just some syntax thing you have to make sure. And then let's have a third variation, which is the same thing, and I'll say child ref and string msg, and we're going to say child ref dot. So with the references, you don't have to do any of that arrow business, and everything works fine. So you have the same method name, but we have 3 variations. And so now, just to show the behavior about stack and heap, there is another memory management aspect, which is what happens when you pass variables in a function, when you call a function with the arguments. So there are 2 types, there are 2 ways they could get passed. The most common type is they get passed by value. So what that means is you give it something and it makes a copy of it by default. It could be different from the other languages because they may pass it by reference. In C++, it makes a copy and then it sends it as the argument on the stack. So if you have something, when you send it, it actually makes a copy and sends the copy. So if you modify something in that function, unless that copy was a pointer, because you have an address, you're making a copy of the address. When you use it, you're going to dereference it, you're not going to change it. It's still going to modify the object. Otherwise, it's going to modify a copy, which is no good for you, because when you come back, that copy has been destroyed. So these semantics are important. So that's why it's important to understand how the function values are passed. And that's why pointers work okay. They don't require special handling, because you pass a pointer to a function and it gets dereferenced. So even though it's a copy of that pointer, it's still okay. So let's just look at an example. So let's say I'm calling a message, change message, and let me pass the object. And I'm going to say changed child object. So I did this, and let's see why. Oh, I have to actually, sorry, my bad. So I have to give them methods so that they can child ref, yeah. Okay, now it's good. So I'll do this, and now at this point I have this child object. You can ignore these 3. So I'm sending this object to this method. It is changing the value on this object. So at the end, when this object is deallocated, I should get this message, changed child object, instead of child object. But let's see what happens. So, okay. So there's a lot of stuff going on here. So let me just clean up a little bit. so that we can clearly understand this behavior. So now if I run this again, so even though I had one object, I just have one object here, and I call a function with that object, what you see happening is that two objects are getting deleted. So what happens is when you call the function right here, a copy is made and sent to the function if the function changes the message of that copy. And then when the function returns, that copy is destroyed right here. So basically that copy was just local to the function change message. What we thought was happening wasn't actually happening. Our object stays unmodified, and that's why it's deleted at the end without any change. So that's how you can see how objects are passed by value. So because it's an entire object, its copy is made, the copy is passed. There's no reference to that object. Now, if you do want the actual object to be passed, what you can do is you can call pointer versions. You can call the pointer version, which is child pointer, and you can say changed child pointer, or you can call the reference version, which behaves the same as the reference. There's no big difference. Changed reference. So at this point, you'll see that only the object is the one which will be unmodified, and everybody else would be happy. So if we do this, so this is the changed child object we saw first. So let's look at it with the code so we can line it up. So this is coming from line 34. It's going out of scope, and that's why you see this. Now when they're deleting the child pointer, it's coming from line 56. The child pointer was changed here, and now it's being deleted. You can see the string is different. Then the child reference is getting deleted because this was the child reference object, and you can see we changed it to child ref. And then at the end, the old child object, which was the original object which we thought would get modified but doesn't get modified, would get deleted. So you can see if you use pointers or references, you can pass in the reference, and that way your target object is updated if there's any change being done in that method. If you want to pass a copy, just pass a copy, just pass an object. If you pass a pointer, the actual object would get updated. So that's it, I guess. That's all about the memory management for C++. There's still a lot of behavior here and there, but I think this covers the basic big bucket functionality, and you can read more about it and then better understand how to use this and how to basically understand code as you're reading, that if a pointer is passed or if an object is passed, you know right away where it would be allocated and how, the method could change it. So thanks for watching. I'll see you next time.